Hello, I'm David. I'm the coordinator of the Maths Learning Centre. It's Semester 1 2023 and this is a revision seminar for Maths 1A. And we've had a chat about what we're going to talk about and we're going to start with determinants. Okay. I'm hoping this won't take too long, but we'll see how we go. A determinant is a thing that you calculate from a matrix, but only from a square matrix. Get a square matrix and you do a calculation and you get a number. That is what a determinant is. It's a calculation you perform on a square matrix and it produces a number. There you go. And you write it like this. The determinant of A, and you'll get a number as the answer. That's how it works. Or you write it like this, vertical lines around the A, and you get a number, which looks like the absolute value does for numbers, but it's not because this is a matrix in here. Okay, that's what determinants are. It's really important to know that they produce a number as the answer. And they are capable of producing any number. They can produce positive numbers, negative numbers, zero. All of them are possible if you put the right matrix in. Okay. A bit of history. Determinants were invented before matrices. Determinants have been around for a couple of thousand years. They exist in ancient China and ancient Babylon. As long as people have been attempting to solve linear equations, simultaneous linear equations, almost that long determinants have existed. So this is a bit of history. You know, you've got equations. It's just an example. Got some equations. You've got as many equations as you have unknowns, and you want to know whether you expect there to be a unique solution or not. And long before people even invented algebra to write equations down with, and they were doing them entirely in words, they invented the determinant as a calculation you could do on the numbers that were involved to tell you whether there was a unique solution or not. And that's how the determinant was invented. And in about 1810, I looked this up a few weeks ago, in about 1810, they named the determinant the determinant. And it's about then that they I can't remember who it was, and that they started writing it as this. With these vertical bars. And that was the determinant. And only after they started writing it like this did people start to become interested in grids of numbers as an object in their own right. And so they went, oh, this grid of numbers, that's an interesting thing. And then matrices were invented in 1840. I think that's really cool. We always teach them the other way around these days. I think it's really cool that determinants are the reason matrices exist. Yeah. And in fact, the word matrix in Latin means pregnant mother. And matrices are called matrices, and this is the truth, because they give birth to determinants. That is why they are called matrices. So there you go. So you learned about matrices for several months before determinants were introduced. But it's the other way around. Matrices were called matrices because they produce determinants. Now these days, determinants are not nearly as useful as they used to be before computers were invented. But it's still really important to know about them, partly for the history and partly because they just turn up every so often. And in particular, they're going to turn up in Maths 1B, if that's a course you do, when you're calculating eigenvalues, which is a thing that's in Maths 1B. So just warning you now, they will come back, which is why it's so important to know about them. And hopefully this video might help some people who are preparing for Maths 1B at the appropriate time to remember how to do determinants. Because your Maths 1B lecturers will assume you just know. Just warning you now. Okay, cool. So the quickest way to tell you how to calculate a determinant is to do one. So my first example is a 2 by 2. If A is like 3, 5, 11, minus 6, just a random matrix, then when you do the determinant, you will calculate the product of those two minus the product of those two. Uh, 80, 91. Cool. There you go. That is calculating determinants for 2 by 2 matrices. Oh yeah, cool. I just wrote 36, didn't I? Look at me. And thank you for listening to what I asked you to do. I could have said that was a test, but it really wasn't. I just make mistakes all the time. I just literally wrote the 3 and the 6, didn't I? Yay. So now that's 50, 70, 73. All right. Cool. Now this will work even if your matrix doesn't have whole numbers in it. We tend to put whole numbers in matrices because it makes it feel easier, but matrices are allowed to have fractions and roots and anything you want inside them. So just wanted to point it out that it's a thing. Okay. I'm going to skip to 4 by 4. No, I won't. I'll do 3 by 3 first. I may not actually calculate the actual final answer here. I just wanted to point something out. So when you calculate determinants, you can pick any row or any column, and those 3 numbers will end up in the calculation, and then multiplied by those will be other determinants. That's how it works. And it's really hard to describe on paper. If you look at it in the notes, there's like a sum sign and little i's and j's and all sorts of things, and that's really difficult to read, and it's much easier to do an example. So I can pick any row or any column that I like, and I am going to pick this row for no particular reason. Pardon me. And this is called expand along. So if you wanted to tell yourself what you did, you would say, I expanded along row 2, or I expanded along column 3, or whatever. That's what you would do. And you need these 3 numbers. So the determinant of B will be these 3 numbers. And in each of these spots, there will be a determinant. And I'm going to put some numbers in these spots here. And it's not just these 3 numbers, you have to put pluses and minuses next to them as well. It's remarkable that anyone ever figured out how to do this, as far as I can tell. It says, how did you come up with this? But anyway, here we are. So we have to put pluses and minuses next to these, and the way to tell which one you want is that the very top left-hand corner of the original matrix always goes with a plus. And every time you switch positions, you'll switch to the other sign. So if I go this way, that one will become a minus. And if I went this way, that would become a plus. And that would become a minus, and that would be a plus and a minus and a plus and a minus and a plus. Or you could go back and forth this way, or up and down, or whatever you thought was best. But just every time you switch positions, you switch to the other sign. Lots of people like to just fill in an entire checkerboard this way and go minus plus, plus minus plus, minus plus minus, plus minus plus. But if I do that, I always write a plus on the next line when it's not supposed to be there, so it's safer for me to just switch from one position to the next. And also, just for the quickness of it, I can start in this zone and then just go down one step and then across this row, and that will, I don't have to fill out the whole matrix to figure out just this row. So that's, I get a minus for this and a plus for this and a minus for this. Okay, cool. And what you put in this spot, I've ruined my matrix now, haven't I? I'm just going to write it again because that's me thinking about where the pluses and minuses come from. What I put in this spot is I cross out the row that I'm currently in, and I cross out the column that this number came from, and I put the matrix that's left, 0, 1, 1, 1/3. And now I cross out the spot where the 6 came from, and it's 3, 1, minus 2, 1/3. And I cross out the spot where the 7 came from, and I get 3, 0, minus 2, 1. There you go. So each number in the row or column that you pick is there, and then the matrix that's next to it is what's left after you remove the row that you're in and the number that you just put there, and the whole column that number's in. How are you feeling about that? Cool. And then you would have to then figure out what these determinants were. So you get minus a half times 0 minus 1 plus 6 times 1 minus 2 minus 7 times 3 minus 0. Oh, look, all my fractions cancelled out. Huh, didn't expect that. That's kind of fun. And so I get a half, except the half, I guess. A half and an 18 and a minus 21. So 18 minus 21 is minus 3 plus a half is minus 2.5, which is minus 5 on 2. There you go. Yay. And that's how to calculate a 3 by 3 determinant. But I could just as easily have chosen any row or any column and it would have come out to the same answer. So let me do another one. One more. The same example but a different way. If I had chosen that middle column that's got a 0 on it, my working would have been ever so slightly easier. So I could have gone, but I'm not going to choose that one because I just want to point out that this process one more time, column 3, so there's my column 3, it'll be plus, minus, plus, minus, plus. So it'll be a 1 times a determinant minus a 7 times a determinant plus a third times a determinant, and then each one of them, so I'll have a half, 6 minus 2, 1, and 3, 0 minus 2, 1, and 3, 0, a half, 6. And then I would have to calculate this. Oh, really, I'm going to do it. I think that's right. That minus 12, 3 minus 0, 18, minus 0, yeah. Oh, and that is the same answer as before because that 12 and that 6 will make this 18 and the rest of it's the same. So it is indeed the same answer as it was before. Awesome. And that will always work. It doesn't matter which column or which row you choose, the process will always produce the same answer, which is really nice. So one last example just to be absolutely certain that we know what we're doing here. Okay. Which row or column should I choose? Row 2, yeah, it's a really good one. It's got 2 zeros and 2 ones. It's beautiful. So there's row 2, and it's a plus, minus, plus, minus. It's going to be starting with a minus for the 0. So the determinant of C will be minus 0, and I'll multiply that by a determinant, but I don't have to because it's 0. Plus a 0, and I'll multiply that by a determinant, but I don't have to because it's 0. Look at me, not even paying attention. Minus, plus, minus, plus. Minus 1, and then I'll have to multiply a determinant, plus minus 1, and I'll have to multiply that by a determinant. All right, and then I remove each spot. So remove the spot where that 1 came from, and I've got 1, 3, 0, a third, 6, 8, and 6, 6, 1. And remove the spot where that came from, and I have 1, 3, 7, 1/3, 6, 17, and 6, 6, 0. And then you would continue, and each of these will have to be done in a similar sort of way. So then I would have to go minus 1 times and another minus 1 times. So this one I have to start from scratch. I don't keep the pluses and minuses from the original matrix, I start from again. So maybe I'll go along the top row, and so I'll have plus 1 times a determinant, minus 3 times a determinant, plus 0. And the determinant for the plus 1 is 6, 8, 6, 1, and the determinant for the 3 is 1/3, 8, 6, 1, and we don't need the one for the 0. And then this one, maybe I'll go along the bottom row there, which will be a plus, minus, plus 6, minus 6, plus 0. And so when I remove the 6, I've got 3, 7, 6, and 17. Remove that 6, I've got 1, 7, 1/3, and 17. And then you would keep going and find what these determinants are, and eventually you'd get to the bottom and you'd be done. That's how it's done. If you're very lucky, your matrix has lots of zeros in it, and it's all lovely. How are you feeling about that? Awesome. And it's totally okay in an exam to put all the little pluses and minuses and circle things and stuff. No one really cares, because if you're not in an exam, you just ask a computer to do it for you, because they're really good at that sort of thing. Okay, so that's how to calculate a determinant, which is lovely. So why do we care about determinants? I already said that. It's because it will tell you whether this has a unique solution or not, if it has a solution at all. So what it says is that, so some theorems. A is invertible if and only if the determinant of A is not 0. I don't know which number in the notes it is, it doesn't matter. That is a theorem. A matrix is invertible if and only if that, which is the same as saying that AX equals 0 has a unique solution if and only if the determinant of A is not 0. So with matrices, when you multiply two matrices together and you get the answer 0, it doesn't necessarily mean that either of them is 0. It's possible to have two non-zero matrices that just have their minuses and pluses arranged in the right way to produce 0 as the answer when you multiply them together without any zeros at all. But what this does mean is that if you have a matrix times a vector and you get the answer the 0 vector, something is 0 and it's the determinant of the matrix A, as long as x isn't 0. So, you know, with numbers, one of them has to be 0. So if we go ax equals 0 and x isn't 0, so just as a corrective, or the other way around, if ax equals 0 for some x that isn't 0, then the determinant of A is 0. So with numbers, if you have two numbers multiplied together get 0 and one of them's not 0, then the other one has to be. Matrices doesn't work, but it does mean that the other matrix has determinant 0, as long as it's a square matrix. Yeah. So this one here is what determinants were invented for, because that's a system of linear equations there. And then when matrices were invented in the 1840s, they applied that and started to think about what that meant for the matrix itself without thinking about it as a system of equations. So, cool. So they're the main theorems about how determinants are connected to other things we do with matrices. But then there's other theorems about how they're connected to the operations that we do on matrices, and they're important too. How are we feeling, though, about what I've said so far? Cool. So, how are determinants related to everything else that you do to matrices? So, tell me things that you can do to matrices. Brainstorm. What can you do to matrices? What's that? Okay, so can do row operations. What else? So what's that? We can add them, yep. Anything else? We can subtract them, awesome. It's a brainstorm. Multiply them, can't divide them, but we can do inverses. Okay. Anything else? It's okay if you can't think of anything else. If you can multiply them, you can do powers. Times by a scalar, yeah. I think that's it. Row operations, multiply them. Have you been taught transpose? Oh, denied. Transpose is lovely. I'm going to mention it anyway, just in case. Transposing a matrix is turning all the rows into columns and all the columns into rows. Yeah, so if you've got a matrix that does this, then the transpose, they do it as a power of t, turns that first column into a row, and that second column into a row, and that, damn it, that was a... Let's do them as boxes, hey? And that third column into a row. And vice versa, you can do it by turning the rows into columns instead. And the really important thing to note is that a single row transpose is a column. Yeah. And some of your lecturers who may not remember that it's not in the course will write this sort of thing when they do subspace things. So just warning you, it will turn up probably in the first week of Maths 1B and they may not remember, they haven't taught you what that means. So now you know. They changed the curriculum in 2018 after the Year 12 curriculum changed, and not everyone's caught up with it yet. I know that's 5 years, but we've had a pandemic in the middle, so, you know, cut them some slack. Okay. So there's our list of things to do to matrices. And let's see how they interact with the determinant. Row ops are great. Row operations are lovely with determinants. And I'm glad you mentioned that first, because it was on the list of things to do. So it doesn't say there, but that was the specific email I got. So here's the rule that if A goes to B, just a second. if you have A and you do a row operation like this, row 1 is replaced with like 3 of row 1, something like that, and you end up with B, then the determinant now will be 3 times the original determinant. So when you multiply one row by a number, it multiplies the determinant, the whole determinant, by that number. Cool. That's great. And the reason that works is because this process back here, if I had multiplied this second row by 2, then there'd be a 2 times a half here and a 2 times a 6 here and a 2 times 7 here, and I can factorise out the 2. That's why that works. And in fact, it even works if you do a column operation. Not that they're a thing, but theoretically they're a thing. It also works for columns. So that's the rule. But it also can look like this instead. I just want to show something that this is true. So if you've got, this is like a before and after way of thinking about it. But you can also interpret it this way. There is a 3 in all of these, and I can factorise it out of that row and factorise it out of the determinant. And so I can go, that's 3 times the determinant of 1, 2, if I want. So this is another way that the working might look, instead of doing a determinant of this is this number and the determinant of this is this number. You can do it that way instead and do an equals, 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 equals sort of thing. How are you feeling about that? Okay, cool. What? Yeah? Yeah? Okay. While we're at it, if you multiply one row by k, then it'll multiply the determinant by k. If you multiply 2 rows by k, it'll multiply by k twice, which is the same as multiplying by k squared. If you multiply 3 rows by k, it'll multiply by k 3 times. So if you multiply your entire matrix by a number, you have to multiply by that number once for each row. So just while we're at it, multiply a whole n by n matrix by k. That means that you multiply the determinant by k to the power of n, because it's once for each row. And that can look like something like this. The determinant of 3a is 3 the n. Well, I can do it with a k, right? This is the symbol version of this thing. Like that. So just be careful. People really often make the mistake of pulling this k out of the determinant, but it has to be pulled out once for every row. And so you've got to have a power of n depending on how big the matrix is. So there's some really Mobius questions in Maths 1A, and there's one that's about determinants and multiplying by stuff. And often people say, what's wrong? And say, oh yeah, that's a 3 by 3 matrix. You've got to have 5 cubed. And so that's why they keep telling you the size of the matrix in that question. Okay, so that's row operations and multiplying by constant. Where's my list? Well, not all of the row operations, just one of them, but we have done that one. The other row operations are swapping 2 rows. And that means you switch the determinant from a plus to a minus or from a minus to a plus. Multiply the determinant by -1. Is that one? And if you add to any one row a multiple of any other row, then it doesn't do anything to the determinant. It stays the same. So if you do operation like, row 3 is row 3 plus 5 of row 1, or minus 5 of row 1, or minus 17 of row 2, or anything like that. As long as this one doesn't have a number with it as well, then determinant is unchanged. So this is something very important. A lot of people, when have learned row operations before, they come to university, and or they are using online resources that are not from this university, be careful. A row operation like this which is very common for people to do, has a minus on the row 3, this will change the determinant. Because this is actually 2 row operations. This is multiplying row 3 by minus 1 and adding 8 of row 2 to it. So this is really row 3 is minus row 3, and row 3 is row 3 plus 8 of row 2. And so what will happen is the determinant of A will be minus 1 times the determinant of A. So be careful. And that is one of the reasons why I do not recommend doing row operations like this. Oh, is it back? Is the mic back yet? Cool, okay. That's why I do not recommend doing row operations like this. And actually, this is not an elementary row operation. This is not. Because the row that you are changing has had something multiplied by it as well. It is a row operation, it's just not an elementary row operation. So. Okay, I think I should do an example using those things. What am I doing? Give me a second. I have no idea what will happen. I have some guesses, but I've got to start. So I'm going to put some unknown variables in here as well, and we will cope. So I know if I do this determinant the long way, I can pick a row or a column and I can multiply everything out. But I choose not to do that because the first thing I notice is that this column, everything has an x in it, because technically that's 0x. So I can factorize an x out of that column like this. That may be the only move that's actually worth doing. And I also notice that if I do row 1 minus row 3, that'll make a 0 here, and that might be useful as well. And that won't change the determinant at all. Yeah, now I probably just have to calculate it. But at least it's made slightly simpler There's only one x and one y in it now. Now, anything else I do will break the 0 that I carefully made. I guess I could do row 2 minus 2 of row 1. Yeah, why not? Yeah, it's probably bad, but anyway. At least now, I can expand along the top, along the first column. Because now it's 1 and all these zeros. So I'll get 1 times this determinant minus 0 plus 0. And so now I've got 3 times 5 is 15, minus x lots of whatever this thing is. 1, 2, 3, 1, 2. And that abomination is the determinant. Cool. That's it. I choose to stop. It's great. So if x is 0, the determinant's going to be 0. And if whatever this is 15, the determinant's also going to be 0. Cool. I'm sure that some of the ones in the Mobiuses and stuff are more productive than that and come out to cleaner answers. But then sometimes they don't, because they don't try very hard to make them clean in the Mobiuses. How are you feeling about the moves I made there? Yeah. If I had done a row swap at any point, then I would have just put a minus in front. And it's okay to write your working as equals 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 like that, rather than do a sequence of row operations and then figure out what happened to the determinant afterwards. I find that harder to do. But you're allowed to do it. I'm going to leave some space here. If anyone wants to ask a question, then do so. Cool. Okay. So we have covered the row operations now. What else is on our list? All right, plus minus times. Okay, so these are the last rules here. The determinant of A times B is the determinant of A times the determinant of B. In your notes, they do this. In your notes, they do this specifically for. Yep.
Can we use subspaces at some point? Out of curiosity. I don't know if it's on the board, but
It is there.
Okay, cool.
We'll see how we go. That's true. In the notes, they do it for elementary matrices first, but it works for all matrices. And because that's true, this is also true. Powers of matrices can be brought out of the determinant as well. And also, it works even for inverses. But just a warning, this is matrix inverse, and this is number inverse, which means 1 over. Like that. Yeah. Whereas this is not 1 over A, because that doesn't mean anything for matrices. So that inverse is for the matrix, and that inverse is for the number. So we did inverses, we did powers, we did times, and the last thing is the determinant of A plus B is, well, who knows, it doesn't actually interact with plus at all. Yeah, it is not determinant of A plus determinant of B. That is that outside, that noise? Okay. Yeah, there is no rule for that. It just doesn't work. Almost nothing expands out over plus, actually, anywhere. So just be aware of that. Cos doesn't, sine doesn't, log doesn't, determinant doesn't. Yeah. Just last one. That's a useful thing to know. That's the same as multiplying by -1. And so that is, I'm going to make that an m there. And that's if A is n by n. So just be aware that when you minus a matrix, it doesn't minus the determinant, it minuses the determinant once for every row. Yeah. And I guess the only other thing to say is that the determinant of the identity matrix, no matter how big it is 1. Because when you do that process, you just end up multiplying all those ones together. And the determinant of the 0 matrix is 0. Oh, and there was one last one, that the determinant of any matrix that is zeros everywhere on one side and you have whatever you want here, that's called a triangular matrix. That will be the product of the diagonal. Yeah. Because all those zeros, when you expand along the rows that have got those zeros, will cause you to have just these numbers at the end. So one of the things that people do with row operations is they try and get it to the point where there's just things on the diagonal and zeros below, and that will, then they can just multiply them together. That is determinants. It's what they are and it's how they interact with everything else. And it is possible to use any of these things to solve problems. So one final call for questions about determinants. Yes, you can do row operations until you get to ones all the way down. Yep. That's right, but every time you do a row operation, every time you do a row operation, it will multiply the determinant by something, and so you get a whole lot of things times 1. Important question to ask, though. Yeah. Sweet. Right, the other thing that I really, really wanted to talk about was slack variables. If I get to 11 and I can go over to do the subspaces, but not too long because there's another seminar after this at 11:30. So, one of the things that people use row operations for is linear optimization. This is officially linear optimization, it's called. So I'm not going to cover the bit where you turn a written statement into a set of inequalities to solve. That's a whole other thing that just going to take a while. But I am going to talk about how the slack variables work and the drawing of the sets. So this idea is that if you have anything like this, and x and y have to be positive, like that, then if you make all of these things true at the same time, what you will produce is a convex set. Even without this bit, it will produce a convex set. So it's not really an example, but it's just a for example. And by convex set in maths, we mean there's a definition which goes that if you join any 2 points in the set, then the entire line segment is contained inside the set. But when you look at it, it just points outwards. That's what it means. That's what convex means. It doesn't have any inwards pointing bits. And then there's another theorem that says that if you have a linear function, like the equation of a plane, its maximums and minimums, when you're only considering a convex set, will be guaranteed to happen at the vertices. But let me just try and draw this set first. It's bad. I really haven't tried in a very good convex set, but here we go. So this is if I draw the bit where it was equals, then this is a straight line if it was equals. And 5, if x was 0, then y would be 8 on minus 7. And if y was 0, then x would be 5 on 8. I'm really going to do a bad job of this. And then that would connect those 2 lines. So this equation number 1, its edge is that line there, inequality number 1. And this one is if x is 0, y is 7/3. And if y is 0, x is 7/2. And it will connect those 2. That's the edge of set number 2 of equation number 2. And this one, if x is 0, y is minus 3, which is all the way down here somewhere. Damn it. Am I going to do it? Yeah, nah. Minus 3 is down here somewhere. And when x is 0, y is 0, y is 3, which is here. That's line number 3. And that is how to draw all the edges. And the question is, which bit of this am I supposed to colour in? And the quickest way is to cross out the bits you don't want. So they're my lines that I had before. They're not straight. They're supposed to be. And that was line 1, and that was line 3, and that was line 2. And you know that with any one of these, one side of it will be the bit where it's less, and the other side will be the bit where it's more. So if I sub in any point that isn't on the line and see what it does, I'll be able to tell. 0, 0 is not on this line, and 5 times 0 minus 7 times 0 is 0, which is less than 8. So this is the good side of line number 1, so I want to cross out all of that, because that's the bad side. And 2 times 0 plus 3 times 0 is 0, which is not more than 7, so 0, 0 is on the bad side of line number 2. Wow, we're crossing a lot out here. And then 0, 0 is not on line number 3, and 0, 0 is less than 3, so 0 is on the good side of that line, so I'll cross this bit out, and what I'm left with is just this bit up here. And so actually it's that bit there. Yay! Okay. Now, that's cool. So these things here, this point here, is called a vertex of my set. This point here is a vertex of my set because it's out at the edge. It's not between any of the other points in the set. And you're guaranteed that if there is some function that is defined like 3x plus 7y or something, the maximum or minimum will have to happen, if it happens anywhere, at this vertex. So that's the theorem. The theorem goes, function f equals like ax1 plus a2x2 plus a3x3 and so on forever, defined on a convex set, if the function is defined on a convex set, then the maximum and minimum of f, if it has one at all, has to happen at a vertex. And what that means is, if you want to find the maximum of a linear function like this, all you need to do is find the vertices and sub them in and see what you get. Okay. So that's the process. The process is sub into f, and whichever one gives you the biggest answer is the one where the maximum is. And whichever one gives you the smallest answer is the one where the minimum is. Yay. Just be careful, if your function goes forever, it may not have a maximum. So. Okay, if there is one. So that's how the process works. The slack variable approach allows you to, without even drawing the function, figure out exactly where all the vertices are. And that's what it's for. I'm going to make my numbers friendlier. No, not this one. But I really want to, when you make up examples, it takes a while. Okay. I'm going to find the vertices of this convex set, hopefully. Or at least get part the way. So the first step of the process is to make sure all of your inequalities are facing to the left, that they're all less than or equal to, which they are. If any of them were greater than or equal to, I would have to multiply everything by -1 to make it face the other way. Okay. So, and then what I have to do is I have to set these up as a system of equations, but they're not equations. So what I'm going to do is I'm going to add an extra variable to say how far away from 6 it really is in this one, and how far away from 8 it is, and how far away from 12 it is. So whatever 2x plus 3y is at the point xy, I want it to be less than 6, and so there's going to be a little bit extra that makes it equal to 6. And it's called a slack variable because it picks up the slack. So this is the next step of the process. And I just think this is really clever. It's quite ridiculous that this is helpful. I've got a problem with 2 variables in it, and I'm going to add 3 extra variables to help me solve the problem. I've turned it from a 2-dimensional problem into a 5-dimensional problem. And it's remarkable that it works. And one of the reasons it works is that this slack variable tells you which side of the line you're on. I'm going to draw a picture. This is an approximate picture of this situation. This is line number 1, and this is the edge of this. The edge of this is line number 2, and the edge of this is line number 3. Oh crap! No, it's not. It's this way around. Sorry. No, it's not. Anyway, it probably doesn't look like this. I'm just going to run with the one I've got. I know that on the x-axis here, that going that way means that y is positive, and going that way means that y is negative. And y being negative is bad because y is supposed to be positive in this story. And I know that here on the y-axis, going that way means that x is positive, and going that way means that x is negative. And x being negative is bad because I wanted x to be positive. And so I already have 2 variables which, if they're positive or negative, tell me if I'm on the good side or the bad side of one of these lines. This is the bad side of the x-axis, and this is the bad side of the y-axis. So what I would like to do is to create a variable that if I'm on the wrong side of this line, then it will be negative. And that's what slack variable number 2 does for this line. So slack variable number 1 is, sorry, that's negative, that's the bad side. Slack variable number 1 is negative on the bad side and positive on the good side. And that's number 2. And slack variable number 1 is negative on the bad side and positive on the good side. And slack variable number 3 is negative on the bad side and positive on the good side. And I really like this as an idea. The reason that we do this is so that later when we figure out what x and y and s1 and s2 and s3 are, if any of them are negative, then I'm definitely on the bad side of at least one of the lines. So places where they are negative, you know when I did this bit and I crossed out all the bad sides? This bit here would have slack variable number 2 negative, and this bit here would have slack variable number 2 and slack variable number 1 negative because it's crossed out twice. And this bit here will have all 3 negative because it's crossed out all 3 times. And this bit, they'll all be positive. And so what I've coloured in here is the places where the slack variables are negative. That's the idea of what slack variables are trying to do. So where were my equations? Just a second. We're in the right order now. So once you've got these, you can turn them into a system of equations. So we've got x and y and s1 and s2 and s3. And there's 2 x's, 3 y's and 1 s1 and no s2's and no s3's, and the answer is 6. And 4 x's and 1 y and no s1's and 1 s2 and no s3's, and the answer is 8. And 8 x's and 1 y and no s1's and no s2's and 1 s3, and the answer is 12. Okay. And I know that these things are not the answers for x, y, z, x, y, s1, s2, and s3. They are just the coefficients in the equations. The answers are here. And at the moment, this says that if x was 0, if I subbed in 0 for x and 0 for y, I would get s1 is 6 and s2 is 8 and s3 is 12. And that means that that point, 0, 0, is in the set because s1 and s2 and s3 are all positive. It's on the good side of line 1 and line 2 and line 3. So that's what that means. And I would like to somehow figure out other x's and y's that are the edges of these things. Okay. So there's one extra piece of information. It is not just true that the bad side of this line S2 is negative and the good side of this line S2 is positive. If you're on the line, S2 is 0. And that means that if you want to be on line number 2, you need S2 to be 0. Which makes sense, because then if S2 was 0, then it would be 2x plus 3y equals 6, and it would be a line. A vertex of this set is a place where 2 of these lines meet. And so you need 2 of the variables to be 0 in order to be on a vertex. This one, that point there, is on line number 2, so S2 is 0, and it's on line number 3, so S3 is 0. And this point here is on line number 2, so S2 is 0, and it's on the x-axis, so y is 0. And every one of these points has 2 of the variables being 0. So what I would like to do is make 2 of the variables 0 at a time and solve for what the other ones have to be. If x and y are both 0, I've already got an answer. If x and s1 are 0, I can row reduce that and get an answer. If x and s2 are 0, I can get row reduce that and get an answer. And I can do it for all possible combinations of 2 of the variables being 0. But instead of doing them all separately, I can actually do row operations on it as a whole matrix. So I could, cross those 2 out, do row operations on that matrix, get an answer, cross them out, do operations on that matrix, get an answer, cross that one out, do operations on that matrix, get an answer, and there'd be a lot of them to do. Or I can do the row operations on this matrix as a whole and then cross the columns out afterwards, which actually makes it ever so slightly shorter. That's the idea. So I have to know how many answers I need to get before I get to the end. And so I need to know which pairs of them are going to be 0. And I've got 5 to choose from, and 2 of them have to be 0. 5 choose 2 is the number of ways to choose 2 things out of 5. And that is how many I know I need to get. So I must choose 2 out of the 5 variables to be 0. And the number of ways to do that is 5 choose 2. Have you seen this symbol in this course? Yeah. And the way to calculate 5 choose 2 is that you get a calculator that has choose on it, like this one, and you go 5 NCR 2, and it gives me the answer 10. The NCR is usually one of the shift buttons. It's not used, doesn't usually have a button of its own. You are not allowed to use a graphics calculator in your exam this year. If in a graphics calculator, it's usually somewhere in one of the menus. It's not actually on the front. You have to go into the probability section. But on a scientific calculator, it should be there somewhere. And it should be called NCR. So in the calculator, okay. But I will tell you how to do it without the NCR button. This number on the bottom, you'll do that number times as long as it takes to get down to 1. So in our case, it only takes 1 step to go down to 1. And then on the top, you'll have the top number, and then you'll have as many pieces as you need to match how many pieces there are here. And 5 times 4 divided by 2 is 10. So just as an aside, not that you will ever need to do this, but just wanted to point out, just for completeness' sake, 4 times 3 times 2 times 1 is 4 factorial. 17 times 16 times 15 times 14. Same number of pieces on the top as there are on the bottom. That is the answer. And then I can cancel that with one of those, and that with one of those, and get an answer that I can get in a calculator if I had one. How are we feeling? All right. Cool. So I know that there are going to have to be 10 vertices to find. I can actually see them all here. 1, 2, 3, 4, 5, 6, 7, 8, 9. I missed one somewhere. 5, 6, 7, 8, 9, 10. I can see them in my diagram, but even if I couldn't draw my diagram, I would know how many there were. And only some of them are actually going to be inside the set, but the quickest way is to find them all. In an exam, they won't get you to find them all. They'll get you to just do 2 of them or something. Or they'll just get you to set up the original equations and you won't do anything, you'll just set it up. They always do part of this for you in an exam because you've only got a couple of hours, and so there's not enough time to do the entire thing. But I'll do one other thing that's worth noting. I could make them 0 and row reduce the rest. No, before I say that, I'll come back to that. As I said, making it up. So here's a table, x and y, and S1 and S2 and S3. Something has just occurred to me. In some of these, they have like x1, x2, x3, and then they call the slack variables x4 and x5. I find it really difficult to remember which ones were slack variables and which ones were original variables, which is why I like to call the slack variables s's and the original variables x's. So, the quickest way to know how many there are is to just make a table of which ones they are. I need 2 of them to be 0, right? This one can be 0, this one and this one can be 0, this one and this one could be 0, this one and this one could be 0. That's all the ones that have x equals 0. Then y and the next one can be 0, y and that one can be 0, y and that one can be 0. That's all the ones with y being 0. And then S1 and S2 could be 0, S1 and S3 could be 0. And then the last one is those 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There you go. I've got them all. And the reason to calculate that 5 choose 2 is so that you know if you've got the right number of them. And as I go, I can fill in what the coordinates of the other ones are. I already know this one. If x and y are 0, S1 is 6, S2 is 8, and S3 is 12. And all of these are positive, so this one's good. All not negative. I will also say that you don't even have to think about them as actually being lines, because in 3D they're planes, and in 3D you need 3 planes to make a point. You don't even have to think about any of that if you don't want to. You just have to figure out how many of the columns you have to cross out to get a square matrix, basically. So if it had been this instead, I would cross out 2 to get a square matrix. If it's this, I'd cross out 2 to get a square matrix. If it was 1 column longer, I'd have to cross out 3 to get a square matrix. That's how many zeros you need. And when you cross them out, that's the same as subbing in 0 for those variables. Okay, so cool. This is the setup, and you would have to find them all if you're going to do it the long way. And then you would go, the ones that aren't 0 are going to need an identity matrix to turn up in those 3 columns. Because when you cross them out, like I did here, this is an identity matrix. It tells me what S1 and S2 and S3 is. If I had an identity matrix in one of the other sets of columns, then it would tell me what X and S1 and S3 is. So instead of thinking about where the zeros are, what we're actually thinking about is where the columns of the identity are going to be. So the other columns, the not 0 columns, you put columns of the identity matrix. And that's where it goes. So I won't do the whole thing. I'm not going to find all 10 of them. But I did want to just show how it works. Putting the headings on this so that you know which variable they belong to is quite useful for filling out your table. Okay, here we go. I've already got S1, S2, and S3. Let's put an identity. I'm just going to show you one that's a little crazy already. All right, I'm going to do Y and S1 and S2 and Y1, Y and S1 and S2. Okay? So the first thing I'm going to think, this is not the best plan probably, but this is where I'm going to start. No, just a second. Nope, that one. I'm going to do that one. So if I want a third column of the identity, it's going to have to be 0, 0, 1. It doesn't matter if they're in the wrong order. So I need there to be a 1 in this spot just here and zeros above it. And that would fill out my third missing column of the identity matrix. I've already got 1, 0, 0 and 0, 1, 0. I can make 0, 0, 1 my missing column. And so I'm going to do row 1 is row 1 minus 3 of row 2. And row 2 is row 2 minus row 3, sorry. Row 2 minus row 3. That's what I'm going to do to get the 1 in the spot. And I'm not going to make this 3 by going row 1 is row 1 minus 3 of row 2, because if I did that, it would destroy this 0 here. So I need to use that one, the one where there's zeros in the other matching spots. So I didn't change row 3. And row 1 is row 1 minus 3 of row 3. So 4 minus 3 times 4 is 2 minus 3 times 4 is 2 minus 12, which is minus 10. Oh, it's 3 times 8. I just did the thing I told you not to do. Right, there we go. That'll help. 2 minus 3 times 8 is 2 minus 24, which is minus 22. 3 minus 3 times 1 is 0, because that was the point. 1 minus 3 times 0 is still 1, that was the point as well. 0 minus 3 times 0 is still 0. 0 minus 3 times 1 is minus 3. And 6 minus 3 times 12 is minus 30. And then row 2 minus row 3. 4 minus 8 is minus 4. 1 minus 1 is 0. 0 minus 0 is 0. 1 minus 0 is 1. 0 minus 1 is minus 1. 8 minus 12 is minus 4. And now I have in these 3 columns the 3 columns of the identity matrix. So if I make x 0, that won't be there because they'll all get times by 0. And if I make, oh, my finger's long enough. If I make S3 0, they'll all be 0 because they'll be times by 0. And I will have that S1 is minus 30 and S2 is minus 4 and Y is 12. So that's this one here. Y was 12, S1 was minus 30, and S2 was minus 4. And that's bad because these two are negative. It's on the wrong side of line number 1 and on the wrong side of line number 2. It's not that you need a diagram, but it's the place where S3 meets the x-axis, which is this point over here. That's outside my set. No, the y-axis. There. All right, anyway. And then you would continue in that zone. You would keep moving identity matrix columns to new positions until you got all 10 of them. So this action of putting a 1 in a specific spot and making the zeros above and below it is called pivoting. I don't know if you've used that word in this course. So what I did is I did a pivot on position 3, 2. That's what this move was called. And if I wanted to do a pivot on position 1, 3, 1, I would have to divide by 8 first. And things would start getting hairy. But I could now, if I wanted to, if I wanted y and S1 and S3, I would need to put a 1 in this spot. Because I've already got those 2 columns, I need the middle column of the identity. So if I wanted this bit here, I'd need to put a pivot there. And I would keep going until I found all 10 of them, and the ones with the ticks where everything is positive, some of them are negative, they would be the corners of the, vertices of the feasible region. Yeah. And then if I had a function that I wanted to find the maximum of, I would sub all these answers in. But these aren't part of the original story. I made the S1, S2, S3 up myself. The actual vertex here is the point 0, 0, and the point on the graph is the point 0, 12. I made these up. They're only there to help me decide if the point is inside the set or not. I don't need them to actually specify where I am on the graph. So the in the notes they call them this entire set is called a basic solution, and the vertex corresponding to it is 0, 0. So I could say and the matching vertex is 0, 0. And this is a basic solution, and the matching point is 0, 12, but it's not a vertex because it's not inside the set. It is a point, it's just not a vertex. All right. It would be good if someone said something at this point. A question or a statement. Yep.
With the matrix, why do we when we like make
why do we keep these ones?
Yeah.
Because we're going to now do more row operations that will need those columns for the other vertices. Yeah. If we threw them away, we wouldn't be able to figure out what the other vertices were. That's why we keep them. That is an awesome question. Awesome. So we keep these ones because we're about to do more of this from what we've got. Yeah, and it means that we don't have to lose any of it.
Doing just like redoing each of doing that.
Yeah, so you could totally pick all possible combinations of 3 and have a whole separate sets of row operations for everything. But what ends up happening is you end up needing about 3 times as many row operations as you would if you had done it this way. Yeah. That's beautiful. Thank you so much. All right, and look at that, we have 25 minutes. So we will talk about the spans and the subspaces and the basis. Okay. All right. So I want to first make you feel like you're not an idiot. Every semester, this is the most requested thing every time. This is the bit that people are just not sure about. So some people are in the, nah, don't talk to me about it. I just don't even want to go there. And some people are it's like, I could do most of it, but I don't really know what I'm doing, and various other bits in between. Are any of those describing you people? Yeah. This is the most pure maths bit of Maths 1A. And it's here for several reasons. One of them is that a lot of people who are doing this course will be doing pure maths in the future. And so has to be some of it in here. And one of them is that the ideas in span, subspace, basis are reused in lots of other bits of mathematics, even bits that don't look like they're pure maths. In particular, differential equations in second year of almost all of the engineering degrees uses some of these ideas. And understanding this will make the other things easier. You can do it without this, but it will be easier with this. And the last thing is, you get to have an experience of what mathematicians are like. So any person who has to learn maths in their degree will have to interact with mathematicians, or at least the things they wrote, at some point in their career, if they're going to use that degree for their career. So as an engineer, for example, there's often an engineer and a mathematician on a really complicated project. And you're going to have to talk to those people, and it's really useful to know how they think. And they really like theorems. You've learned that, right? And they love definitions. And now you know. So teaching you some pure maths in first year gets you to know what mathematicians are like, so that you can talk to them more easily, you can understand what it is they're trying to say more easily, you can have compassion on them, and just the world is a better place. Okay, that's the philosophy, but now I'm going to talk about it. And I have to say to you, I warn you now, this is my favourite bit of Maths 1A. I love subspaces, but not to say that you have to love them too. But you do have an exam that will talk about them. So whether you love them or not, approach them, okay? But you can let me love them for you, okay? Right. So Cool. Right. I'll see how far I get. I'll try and get the most important things. And the very most important thing to say first is that to a mathematician, a vector is not a point and it is not an arrow. It is just a thing that does linear combinations. I put it in inverted commas. To a physicist, a vector is an arrow. It's like a force or something, or a displacement. To a mathematician, a vector is just a thing that adds to other vectors and can be multiplied by scalars. That's what a vector is to a mathematician. And nothing gets to be called a vector unless there's a whole lot of other vectors that are with it to be vectors together. So vectors are things that together do addition and scalar multiplication in a reasonable way. Where by reasonable I mean you can expand out brackets and do multiplication in any order you want and you'll still get the same answer and those sorts of things. I say this now because here in first year, vectors are always sets of coordinates. Now, for example, a set of things that all have numbers in those positions where these are real numbers that's a vector because all of them together are vectors, and this is called a vector in R4. The R is referring to the fact that they're real numbers, and the 4 is referring to the fact there's 4 coordinates. And the entire of R4, all of those things together, which are these things with 4 coordinates, they are together called vectors. And they're called vectors because I can add 2 of these things together, and I can multiply one of those things by a scalar multiple and get another vector. And I can do the adding in whatever order I want, and I can subtract, and there is a 0, and there's all these other rules that work. But in other courses, other things get to be called vectors. For example, matrices. You can add them together, you can multiply them by scalars. They behave the way vectors behave. So to a mathematician, they can, on a good day, call them vectors. Functions do that too. I can add functions together, I can multiply them by scalars, I can call them vectors if I want. Now, we don't do this in Maths 1A, but it's coming in second year courses. All right, just warning you now. All right. And everything we learn here about vectors, which are things with coordinates, we can borrow and use for those other things. Okay, cool. So that's what vectors are. But really importantly, a set of coordinates like this can simultaneously represent either a point or an arrow, depending on what we want to do with it today. It can either represent a point or a journey. I can say this vector could be the journey from one point to another, or it could be an actual point. And mathematicians are not going to be very particular about which one of them they're representing at any moment. You get to decide, depending on what you want it to be today. Okay. And when I talk about a journey, I just want to make sure that we've all got this right. Just remember, when you first learn to add numbers, and you had like 8 plus 4, maybe 8 plus 3, maybe not when you first learned to add because you just put blocks together, but 8 plus 3, you'd go, okay, 8, 9, 10, 11. And the 3 was a journey. It was how many of those moves to make. And the 8 was a starting place. And so already numbers are points or journeys, depending on whether it's a place to start or a thing to do. And vectors do that as well. So you can think of this like 1, 5 plus minus 1, 2, for example. There is the place 1, 5. And, damn it, let's do 1 minus 2 because then it'll fit on my picture. And there is the journey 1 minus 2. So that's the place 1, 5. And that's the journey 1 minus 2. And then this new place just here is the answer. 2, 3. You get to decide. I could have done it as the place 1, 2 plus the journey 1, 5, and that would have gotten to the same location. Yeah. Cool. That's not that important, but it is for helping to imagine what things look like. And the other thing to know is, if a point is ever sitting all on its, a vector is sitting all on its own, not doing anything, it's usually being thought of as a point and not an arrow. Right. Right. So, the thing that we can do with points is draw graphs. We're good at that. We can draw graphs, or graphs if you like, with points. And there are two ways to do that. You can tell someone every point that is in the picture. You can tell someone how to make every point in the picture. Or you can tell them a formula to decide whether a point is in the picture or not. So I'm just going to talk about sets. A set is a set of vectors is a collection of vectors that has a rule for deciding whether you're in it or not. And you can colour them in. And most sets, so you've been making convex sets in the course already. And the people who design this course think that that is a nice lead-in to subspaces, but it's not really. But I can see why, because you colour in points, and the decision rule for being in a convex set is that when you sub it into all these formulas, it works, right? And you can cross out the ones that aren't in, and you can colour in the bit. And all of these are coloured in because no matter which of these points I sub into those formulas, they all produce the correct answers. They all produce something that's less than 8 here, and something that's more than 7 here, and something that's less than 3 here. And that is one of the ways to make a set. You can have a rule type of thing, and then a such that sign. Some lecturers will write a colon in that spot. I like to write a vertical bar because my colons might just look like a random scratch on the page. And then a rule to satisfy. And examples of this kind of thing are x, y, z in R3, such that x minus y plus 2z, 8z is 0. That's a set. And the way to figure out what that set looks like is to find random points and sub them in and see if they come out to 0 or not. And if they do come out to 0, they're in the set. And if they don't come out to 0, they're not in the set. And if you colour in all the ones that come out to 0, you will get an object, which will be a plane in R3. And I will say now that it is not R2. It's a plane in R3. R2 is made of things that have 2 coordinates. And all of the points on this plane have 3 coordinates. So they are not in R2. You can be forgiven for thinking that that is how to talk about it, to say it's R2, but most mathematicians will not forgive you for long. So R2 is definitely a plane, but most planes are not R2. They're just planes. So it's just a plane. It's in R3. Okay. So even if this hadn't been a 0, but had been like a 10 or a 20 or a -7 or whatever, it would still have been a plane. Okay. But it wouldn't have contained the 0 vector, which in our heads we know is really the 0 point, the origin. Okay, so that's one way of making a set. And this rule doesn't have to be equations. It can be anything as long as it is a rule that you basically sub this into to figure out if it's the answer. Figure out if the answer is correct. And you can have lots of equations. You can have a whole list of equations here, and there could be several of them, and they can all be needed to make the set. So you can have more than one, right? Something like that. The set of vectors in R3 such that x squared plus y squared is 0 and z is 7. I could totally have just put a 7 here and just remove that entire thing, but that's the idea. This is, well, this is actually a line, by the way. It's a vertical. No, it's. Oh, this is a single point. This thing. If you colour in all the points that satisfy this, you only get 1 point. It is the point 007, by the way. Because the only way for x squared plus y squared to be 0 is for both x and y to be 0. Because x squared is a positive number and y squared is a positive number. If you have anything other than 0, you'll get a positive answer and not 0. So this means x and y is 0 and z is 7. So like this is just the point 007. But point is, there was a rule to decide, and it is possible to try and figure out what all the points were. All right, so that is one way to make a set. I have mentioned another way to make a set, which is literally just to list the points that are in the set. And this is literally just 3 dots. That is what this set is. It's not connected up, they're just 3 dots. Like this is literally just, that's x, y, and z. This dot, and this dot, and this dot. And that is all there is. So, and the last type of set is some sort of calculation or construction, you know, a way to make the thing such that some details. So it's the same notation, but it will be interpreted slightly differently. So for example, this is one of these kinds of things. It says the vectors s and t plus 3s and 2t such that s and t are in R. This is how to make the thing, and these are the details to say what those letters stand for. And that is quite different to this kind of set, like in terms of the way that we're writing it. In this kind of set, you don't give any details, you don't know how to tell if something's in the set until this part, Whereas in this type, this is how to tell if something's in the set, if you can make it that way. And this gives me a rule for how to tell. If I get a random point, I can sub it in. If it comes out to 0, it's in the set. If it doesn't come out as 0, it's not in the set. Whereas this, the only way to tell if something's in the set is to attempt to make it this way. And if it's possible to make it this way, then it's in the set. And if it's not possible to make it this way, it's not in the set. Which makes it hard, because what if I just can't make it this way today because I'm not on my best game, and so I can't tell that it really was after all? That makes it quite difficult. But it does tell me all the points in the set. Whereas this one, it was quite difficult to tell that the only point in this set is that point. So this is good for deciding if points are in the set, but bad for telling you what the points actually are. This is good for telling you what the points are, but it's bad for deciding if a point is in there. They are the two main ways to make a set. Okay, cool. The reason I talk about this is that subspaces are a kind of set. And the kind of set that they are is a set that works as a collection of vectors all by itself without the rest of space. It's self-contained with respect to the things that vectors do, which is scalar multiplication and addition. That's my word, self-contained, but the maths word is closed. Under addition and scalar multiplication. So that's what a subspace is. That's the definition of a subspace, that no matter which vectors you pick inside it, by which we mean points, if you add them or do scalar multiplication, you will end up still inside the subspace. You can't escape a subspace by doing addition and scalar multiplication. So if you're self-contained or like inescapable, if you can escape the set by doing additional scalar multiplication, it's not a subspace. And that's great. You know, it's a beautiful definition. Mathematicians love definitions. A set W is a subspace when for any U, damn it. There are 3 rules. I'm just going to do the formal definition, and I'm about to tell you what things count as subspaces and what things don't without having to check the definition. But we need the definition first. And there are 3 rules in the definition. There is rule 0 and rule 1 and rule 2. And rule 0 is that the 0 vector has to be in there. Technically, you don't have to have the 0 vector. I mean, the 0 vector will be in there if it's a subspace. But technically, you just have to check that it has any vector in it at all, and that will do fine. And that's what the definition is in Algebra 2. But the definition in Maths 1 is just the 0 vectors in there. But I just want to say, if you Google definition of subspace, it may not have the 0 vector rule. It may have the non-empty rule. Just wanted to point it out. So that's why I call it rule number 0, because it's about the 0 vector. And rule number 1 is that if there is a vector in the set and a number that is a scalar, then when you multiply the vector by the number, you are still inside the set. And this symbol means is in. Some people call it is a member of, but most people pronounce it as is in. And rule number 2 is if you have 2 vectors that are both in the subspace, or possibly the same vector twice, it has to work either way, then when you add them together to get a new vector, that point is still in the set. In your notes, they write these the other way around, but it logically makes sense to me that this one is rule number 1 because it only refers to one vector, and this is rule number 2 because it refers to 2 vectors. This is the easiest one to check because it only needs 1 vector, whereas this one needs 2. So, all right. So, I could do proofs. There are lots of examples of doing proofs, but the most important information I want to tell you right now is how to decide if something is a subspace or not without having to check all of those rules. Because there are things that are definitely subspaces without having to check. And I know this because in your notes, there is a page of notes which describes things that are subspaces, and you won't have noticed it because it doesn't say the word theorem anywhere on the page. But they are theorems. And I need to say this now because in Maths 1B, they're going to assume you know those not theorems because they're not going to mention them in the Maths 1B notes. So just now, in the future, make sure you keep that page for Maths 1B. Okay, or this page. So these 3 ways of describing a set each have a kind of thing that is definitely a subspace. Things that are subspaces. If you've got a set that's described as a list of points, you know, just a short list of points, the only way that can possibly be a subspace is if the list of points is just the 0 vector. Or if you like this is the other way of writing it without referring to the specific coordinates. That works just as well. No other list of points will be a subspace. Do you mean with a plus sign? Not a subspace. Good question. It's not a subspace. Now, let's just check. This does in fact contain the 0 vector, so it does satisfy rule 0. But if I multiply this point by 2, I will get 1, 6, 14, which is not in the list. And so it's not, I can escape it by multiplying by 2. That's why no other list will be a subspace, because unless it contains everything that's a multiple of this, it's not going to be a subspace. So just satisfying this rule isn't enough. You have to have all 3. And just to check the 0 vector, if I have the 0 vector, it's in there, great. And if I multiply this by any number, I just get this back again, so it can't escape it by multiplying. And if I add this to itself, I just get this again. I can't escape it by adding either. This can't be escaped by doing any of these things, so it's a subspace. It's the smallest possible subspace. They call it the trivial subspace, because to a mathematician, trivial means involving 0 usually. To the rest of us, it means the unimportant one, but it's almost like the most important one because it's the smallest. Okay. So do not be fooled just because it's got the 0 vector in it. So I'm so glad you brought that up. Awesome. Let's do this type of thing now. The rule to satisfy version of your set. Vectors in Rn, it'll be something like that, such that homogeneous linear equations, it doesn't matter how many homogeneous linear equations it is, as long as they're linear, meaning there's no squares or no multiplying the variables by each other, and homogeneous meaning it's equal to 0, there's no just floating constants, that is guaranteed to be a subspace. but not homogeneous and not linear or not an equation, almost always not a subspace. There are some ones where it's a technical detail and it turns out to be one after all, but almost always, if it's not an equation, if it's an inequality, it's not a subspace. If it's not homogeneous, it definitely won't be a subspace because zero vector won't be in there. And if it's not linear, usually not. So just as an example, x, y, z, such that x equals 0 and x plus y equals 0, subspace. Because these are homogeneous linear equations. Done. If someone asks you to prove this is a subspace, then you have to go through the rules. But if someone just asks you, is it a subspace, give a reason, then you would say it's a subspace because it's the solutions to homogeneous linear equations. And that's the whole answer. If someone just asks you, is it one? But something like this, not subspace. It's not homogeneous. Because the zero vector isn't in there. X minus 3y is 7, not a subspace. Since 0, 0, 0 is not in it. Don't even need the Z. Let's do it in R2. Also, not subspace. This is not a linear equation. And I know what this is. This is like that. And it does contain the zero vector, but it contains this point. And if I multiply that point by 2 as a vector, I escape the set. Actually, something like this. This is still a plane, right? A plane that doesn't go through the origin is the worst kind of not subspace. It breaks all 3 of the rules all the time. It is impossible to pick a vector inside this so that when you multiply it by a number, it's still in there. Because it's like, there's the origin, it's here. All of those vectors, if you times them by 2, will all end up over here, which is not in the set anymore. And if I add 2 of them, that little triangle will add up over here off the set. Like, you can't add vectors that are in this and get a vector that's in there. It is the worst not subspace that there is. If you want to guarantee that you will break all 3 of those rules all the time, just change the 0 to any other number. That's one of my favorite facts about subspaces. Okay, cool. So what it means, if someone gives you a list of like 6 subspaces and 6 sets and says which of them are subspaces, you can go and write, all right, homogeneous linear equations, not homogeneous, not linear, great, done. So just psych, if this, sometimes if there's x squared and in there, it does come out to be a subspace after all. I just want to point the last one out, but just that one, x squared plus y squared equals 0. The only way to satisfy that is for x and y to both be 0. And so you get the x and y has to be 0, and the z can be whatever you want. And that is a subspace, because it's the z-axis. And I know that I can't escape the z-axis by adding 2 things on it together, because they'll still be on the z-axis. And I can't escape it by multiplying by things, because they're still there. So just psych, it is a subspace after all, even though it wasn't a linear equation, because the only solution to that is mainly 0. So just, yep. It's the only one I can think of. I'm sure there are others. You just have to be able to turn your quadratic into a linear equation, a couple of linear equations. Because this is really the same as this. The other way of doing this is x, y, z such that x is 0 and y is 0, and they are homogeneous linear equations. So, okay. It's the only one I can think of. There may be others, but they'll only happen if all of the terms have the same power, like they're both squared. Yeah, but even then, it usually won't work either. So just, if someone had to make you, if you had to guess and you weren't allowed to give a reason and you weren't allowed to do any calculations, if you saw a non-linear one, I would just guess that it's not. Would be my rule. Okay, and the last kind of set is the one where you describe what the points are. Feel free to leave if you want to go. The last kind of set I'm just going to say it. The span of vectors is a subspace. Always. And what span means is all the linear combinations of those vectors. And what linear combination means is number times vector plus number times vector plus number times vector. And so just as an example, S times 103 plus T times 587 such that S and T are in R. Number times this plus number times this for all the possible numbers I could possibly have chosen. This is the span of 103 and 587. Therefore, it's a subspace. That is what span is for. So in this course, they tell you the word span in about week 2, I think, maybe week 3. And then about 3-4 weeks later, they define subspaces. Span is the fundamental thing that a subspace is, right? The point of a subspace is that when you do linear combinations, you do addition, scalar multiplication, you can't escape. And the best way to not escape is just to include all of them. It's got all the combinations, so I can't escape because I've got them all already. That's the idea behind it. And it just want to point out, just to be sure, the thing that I said before, this one I said when I was talking about this kind of set, S, T plus 3S, 2T, such that S and T are in R. Well, that's the same as S lots of 1, 3, 0, and T lots of 0, 1, 2. Which is a span, and therefore it's a subspace. Yay! So if you can rewrite your expression in such a way as this, then you can tell it's a subspace. And you already have, by the time you learned about subspaces, you had been practicing doing this move when you solve linear equations. And so this is actually the proof that homogeneous linear equations do define subspaces, because you know that when you solve AX equals 0, you always get something like this, which is a span, which is a subspace. Yay. How are we feeling? So here we go. Let's look at some not subspaces, because we need to know some things that aren't subspaces just to make sure. If it doesn't have all the linear combinations, it's not a subspace. It has to have all of them. That is not a subspace. it doesn't have all the multiples of 587. It's only got this one. So because it doesn't have all the combinations, it's not a subspace. Now, it's quite hard to tell proof-wise that it's not, but this is a line that doesn't pass through the origin, and we already know that flat things that don't pass through the origin can't be subspaces. And yeah, it doesn't go through the origin because it's not, so it's not a subspace, but it doesn't have all the combinations. If I want this to come out to be the 0 vector, I can't do that because no matter what, the middle coordinate is 8. So no matter how many of these I add, the middle coordinate will always be 8, so it doesn't contain the 0 vector. And what about this one? That doesn't have all the combinations either, because I'm only allowed to use whole numbers. I'm supposed to be allowed to use, to do a linear combination, I'm supposed to be allowed to use any real number, including like a half or √2. So, for example, I can't do half of this vector and still be in the set. But I'm supposed to be able to do any multiple. So there you go. Now you can look at the way it's written and have a really good guess about whether it's a subspace or not. And sometimes you will know for sure. So one of the points of spans is, like, its purpose is to make subspaces. That's what it does. It turns a list of vectors into a subspace. So just pointing one last thing out, just the points 1, 3, 0 and 0, 1, 2 all by themselves, they are not a subspace, as it's only 2 points. Whacking a span in front of them will blow them out into infinitely many points and turn them into a subspace. That subspace does contain the points 1, 3, 0 and 0, 1, 2, but it also contains 2 of this and 2 of this and 7 of this and minus 16 of this and half of this, and all the combinations are in there somewhere. Yeah. So I am going to actually have to stop because I have another seminar at past, but I will say one last thing. When they talk about basis, which is a whole other thing, and there will be subspaces on it, the point of a basis is to be these vectors that make your subspace into a span. So if you have subspace W, and you rewrite it as W equals the span of something, that bit, sorry, subspace W, you rewrite it as W as the span of something, whatever's in that spot, that's the basis. That's what a basis is for. To rewrite your subspace as the span of something. And it's technically not a basis unless that list is as short as it can be. So they have to be basis if they're independent. But the whole point of a basis is to rewrite it as a span, which means you'll be able to take something that was a list of equations and turn it into a span, which means that you can find all the points in the thing. Yep?
Would that thing in the middle be vectors?
They are vectors, yes. Okay. Thank you so much. I wish you clear thinking and calm nerves during your exam.